Hi, I'm Grace, and today I'm going to be talking to you about filters and frequency response curve. In EEG, we use filters to help us decrease the size of unwanted frequencies and enhance frequencies that are more likely to be cortical activity or brain activity. So we have two different kinds of filters we use. We have a high pass filter that passes high frequencies through, and we have a low pass filter which passes low filters through. How you also might hear those referred to is a low pass filter is also called a high frequency filter, and a high pass filter is also called a low frequency filter. So our low frequency filter is what sets the low end of the bandwidth. It filters slow potentials and it allows the faster potentials to go through. Vice versa, our high frequency filter sets the high end of the bandwidth. It filters our faster potentials and allow low frequency to pass through. With our filters, like I said earlier, it's important to enhance brain activity and try and attenuate, get rid of artifact, anything that is not brain activity. When we put a filter on our EEG, it will not only affect the specific frequency we're targeting, but it will also affect the surrounding frequencies. The extent to which these neighboring frequencies are affected is demonstrated by something called the frequency response curve. The frequency response curve is a graph of frequency and amplitude. So this is our graph our teacher gave us. The curved lines are representing how the filters are affecting different frequencies, and then the percent of amplitude we are seeing is shown on this axis here. This is the graph that I drew for class. The curved lines are the filters, and as you can see, they're named by which frequency is attenuated 20 to 30%. So for example, 0.3 hertz is attenuated 20 to 30% by the 0.3 filter. On EEG, the standard filter setting is a low frequency filter of 1 hertz and a high frequency filter of 70 hertz. So our low frequency are these light blue over here. So our standard is this 1. And then our high frequency is the dark blue on this side. And our standard is 70. So that is over here. A low frequency filter of 0.3 instead of 1 is going to allow for us to see slower frequencies. And we can see that demonstrated in the graph. So at our standard 1, if we have a frequency of 0.5, it's going to be only showing 50% amplitude of that frequency. So it'll be attenuated 50%. But if we lower our filter and we use a 0.3 filter, then that same 0.5 we can now see 100% of. So that would be an advantage of lowering the low frequency filter. When we lower our low frequency filter, it allows for us to see slower cortical activity in cases such as stroke or a patient that has a tumor. But we need to also take caution in things that have slow skin potentials like sweat, because that can mess up what we're looking at. When a patient has a lot of EMG artifact or muscle artifact, we can set our high frequency filter to 35 hertz instead of 70 hertz, and that allows us to filter out that faster activity so that we're only seeing things that are more likely to be cortical activity. So, for example, if we have 60 hertz showing on our study and we have and go up to our standard 70 filter, we are still seeing about 80 to 90% of that fast frequency. But if we lower our high filter to 35 hertz, then that 60 hertz is now only showing 50 to 60%, so it allows for a clearer image of the cortical activity. While that can be helpful at times, it is important to know that it can also attenuate spike activity. And it can affect other things on EEG, such as sleep, spike and wave. So it's important to understand that you could be missing things and that the wave morphology can change when lowering that high frequency filter. Thank you for watching my video. Just remember that filters allow us to enhance brain activity and attenuate artifact. And our high frequency filter can also be called a low pass filter because it allows low frequencies to come through. Our low frequency filter can also be called a high pass filter because it allows high frequencies to come through. And our frequency response curve is going to help us have a visual of how our neighboring frequencies are affected by the different filters. Thank you so much.